Hello everyone, and welcome to the very first video for Math 335. As you know, there will be one of these videos for every class meeting, covering the basics of what you'll need to know in order to dive deeper in that day's class. This video will get you ready for our meeting on Wednesday the 26th. Now, before I begin, I encourage you to grab a pencil and paper or whatever your preferred note-taking device might be. It's likely that you'll have to pause and rewind this video a whole bunch in order to give yourself time to take notes, but please do that as much as you need to. The topic for this video is modular arithmetic, which we began to discuss in Monday's class. Now, hopefully this topic feels at least a little bit familiar from a previous class, for example, Math 301, which I know many of you took at SF State. But regardless of your familiarity, we'll take some time today to review what you'll need to know going forward in this class. So remember, in Monday's meeting, we discussed the basic definition here. What we said was that the statement A is congruent to B mod n means, at least roughly, that you can get from the number A to the number B by adding or subtracting n's. Now I want to return to that definition and make it a little bit more precise so that we have something a bit more concrete we can check to see whether or not it holds. Actually, before I'm ready to give you a more precise definition of the statement A is congruent to B mod n, I first need to give you an intermediate definition, which is the definition of what it means to say that one integer divides another. So here's that. If C and D are integers, we say that C divides D, and I'll write that with this vertical line here. We say that's the case if D is equal to C times K for some integer K. Here's a couple of examples just to make sure that we see what this terminology means. For instance, I'd say that 2 divides 6 because 6 is equal to 2 times an integer, namely 3. Or I'd say that 4 divides 20 because 20 is equal to 4 times an integer, namely 5. But on the other hand, 3 does not divide 7 because 7 is not equal to 3 times k for any integer k. Okay, so now that we have this definition of what it means for one integer to divide another, we're ready to use that to give a precise definition of congruence modulo n. Here it is. In precise mathematical notation, we'll now say that the statement A is congruent to B mod n means that n divides the difference, A minus B. For example, here's a true statement. 5 is congruent to 1 mod 2. Now, based on our rough definition, we believe this to be true because we can get from 5 to 1 by subtracting 2 twice. But now, based on this new definition, we have something even more concrete we can check. We should check that n, which in this case is 2, divides the difference 5 minus 1. Well, 5 minus 1 is 4, and it's indeed true that 2 divides 4 because 4 is equal to 2 times an integer. Here's another example. 2 is congruent to 17 mod 5. Why is that? Well, 5 divides the difference 2 minus 17 because 2 minus 17, that's negative 15. And 5 does divide negative 15, given that negative 15 is equal to 5 times an integer. It's equal to 5 times negative 3. So that's the definition of congruence modulo n. Now let's take a closer look at one other thing that came up briefly in Monday's class. And that's the fact that any number is congruent modulo n to some number in the range from 0 up to n minus 1. Here's an example of what I mean by that. Let's say I'm working modulo 12, so n is 12, and I want to ask, what is 26 congruent to mod 12? And specifically, I'd like to fill in this blank with a number in the range from 0 up to n minus 1. So in that case, this means 0 up to 11. To figure out what to put in that blank, one way to go about it is to start from 26 and repeatedly subtract 12s from it, or add 12s to it if you need to, until you wind up in the range you want to be in. So, for instance, 26 by subtracting 12 once is congruent to 14 modulo 12. And well, I'm not yet in the range I want to be in, so I'll subtract 12 again. 14 is congruent to 2 mod 12. And now I've done it. I've gotten a number that's between 0 and 11, and so that's what I'll put in the blank. This process that we just went through of starting with any number and then replacing it with something in the range from 0 to n-1 to which it's congruent is called reducing modulo n. So in this example, I'd say that what we just did is we reduced 26 modulo 12. Now, one kind of weird thing about that terminology reducing is that I'll still call it reducing, even though potentially I might start below my desired range and have to bump the number up to get there. For example, suppose I'm trying to fill in the blank in this equation with a number between, well, 0 and n-1. In this case, since n is 5, that means I want to fill it in with a number in the range from 0 up to 4. Now what I'll do is I'll start with -7, and I'll repeatedly add 5s until I get in my desired range. First, by adding 5, I see that -7 is congruent to -2 mod 5, and then by adding 5 again, I see that it's congruent to 3 mod 5, which is in my desired range. So again, even though we had to replace -7 with a larger number to fill in that blank, I'll still refer to the process that we just went through as reducing -7 modulo 5. Where this idea of reducing modulo n is going to be really useful for us in this class is when we bring the arithmetic into modular arithmetic by starting to add or multiply numbers modulo n. So here's what I mean by that, and what I think of as sort of the main punchline of today's video. Given any two elements of the set of numbers 0, 1, 2, and so on up to n-1, we can add those two things modulo n and reduce the result to get a new element of that same set. So for instance, let's see what this says in the case where n is equal to 5. When n is equal to 5, we're adding elements of the set 0, 1, 2, 3, 4 modulo 5. For instance, if I want to add the elements 1 and 2 from that set, I can do it. The result is 3, which is another element of that same set. On the other hand, if I try to add the two elements 3 plus 4 in that set, I'll initially get an answer of 7, which is outside of the set, but I can reduce 7 modulo 5. When I reduce 7 modulo 5, I'll get 2, which is again back in my set. We're going to think through this idea some more and play with it in a whole bunch of examples when we meet over Zoom on Wednesday. Don't forget to take a look at the comprehension question on this video's material before then. Remember, you don't have to get the question right, you just have to attempt it in order to get credit. Okay, so see you in class on Wednesday.